Back Physical Science 20. This is the PW1.6 section, wave applications, and for that we're just going to do the Doppler effect. So we'll look at, describe what pitch and loudness of sound depend upon, and provide an example of an application of the properties and characteristics of waves such as the Doppler effect pertaining to sound and light waves. So pitch, first of all. Marin, Mersenne, and Galileo were first to determine the pitch we hear depends upon the frequency of vibration. Pitch can be given a name on the musical scale. For instance, middle C has a frequency of 262 hertz. The ear is not equally sensitive to all frequencies. Most people cannot hear sounds with frequencies below 20 hertz or above 16,000 hertz. So the higher the note, the higher the frequency. The lower the note, the lower the frequency. So older people are less sensitive to frequencies above 10,000 hertz than are young people. By age 70, most people cannot hear sounds with frequencies above 8,000. This loss affects the ability to understand speech. So pitch has to do with frequency. Whether it's a low note or a high note, that corresponds to low frequency and high frequency. Loudness, so if we were to draw a little sketch, let's say we have a waveform that looks like that. So of course we know that wavelength is the shortest distance between corresponding points, so maybe crest to crest. So this would be high frequency and a very small wavelength compared to if I drew something that looked like this. So wavelength would be this. So you could see it would be high wavelength and low frequency. And frequency has to do with how many cycles past a given point per second. So if I was to look here, I have 3 cycles in this region. Whereas if I take that same region, I may have 1 cycle. Okay? Loudness. Frequency and wavelength are 2 physical characteristics of sound waves. Another physical characteristic of sound wave is amplitude. Amplitude is the measure of the variation in pressure along a wave. In humans, sound is detected by the ear and interpreted by the brain. The loudness of a sound as perceived by our sense of hearing is related to amplitude. So if I was to look at this, from rest position, if you recall, amplitude is the maximum distance from rest position. So we would say quiet, low amplitude compared to, if I look at this, the distance from rest position, this would be considered louder because it has a higher amplitude. Okay, so those are the differences between pitch and loudness. The Doppler effect. Now I have a video posted there involving a Doppler effect demo. And in it, it talks about how this is, how we perceive it in terms of sound, and then of course how we perceive it in terms of light. Have you ever noticed that the pitch of an ambulance, fire, or police siren changes as the vehicle speeds past you? The pitch is higher when the vehicle is moving towards you. So the pitch is higher, which means frequency is higher than when it's moving away from you. This frequency shift is referred to as the Doppler effect. So in terms of a moving source, if we just simply had something not moving and was making a sound, we would see this. Both people would register the same frequency, the same cycles per second. But if I move this towards one person, we can see the waves that are generated by the source in the video, and the demo is very good for showing this, get bunched up. So there's a high frequency here, and then there's a low frequency here. Less cycles per every second. So if I was to take this area right here, there's 1, 2, 3. If I was to take that same area here, there's around 10. So the parent shift in frequency is what we register there. So if you look at the source S moving to the right with the speed of Vs, so the source velocity or speed The wave that emits spread in circles centered on the source at the time it produced waves. As the source moves toward the sound detector, observer A in the figure above, more waves are crowded in the space between them. The wavelength is shortened, and because the speed of sound has not changed, more crest reach the ear per second. And of course, that corresponds to an increased frequency. And when the source is moving away, we can see the wavelength gets longer, and there are less waves passing by per second because they're so big. The frequency is lower, less cycles per second because the wavelength is bigger. This illustrates the Doppler effect for a moving source of sound on water waves in a ripple tank. That's what's on the right hand side. It's not a very good diagram, but you can see how the waves get bunched up here and spread out over there. A Doppler shift also occurs if the detector is moving and the source is stationary. In this case, the Doppler shift results from the relative velocity of sound waves and the detector. As the detector approaches the stationary observer, the relative velocity is larger, resulting in an increase in waves. So you can either you'd get the same scenario if this thing making the sound was stationary and this person moved towards it. We would get a bunching up of waves again, a higher frequency area, so a higher pitch. So as the detector approaches the stationary source, the velocity is larger. As the detector recedes or moves away from the source, then the relative velocity is smaller, resulting in the decrease in wave crests, and it would be a lower pitch sound. For both moving source and moving observer, whichever one, the frequency that the observer hears can be concluded with this equation right here. So the subscript D represents detector, the subscript S represents the source making the sound. So just V is the velocity of the sound wave in air that day, involving the temperature, etc. VD is the detector speed. So in the previous example, the detector was not moving, so it's going to be 0 sometimes, but sometimes it can be moving. And VS is the velocity of the sound source. And of course, the frequency is the actual frequency that the source is emitting, and FD is the one that we're calculating. What does the frequency appear to be due to this movement? So this equation applies when the source is moving, when the observer is moving, or when both are moving. It corresponds to all of it. And if no one is moving, you just simply use 0 for V. As you solve problems using the above equation, be sure to define the coordinate system. This is a key thing. Put a star right here, so that the positive direction is from the source to the detector. So always draw it so the detector is on the right of the thing making the source. So just like this diagram, this item here is making the sound, the detector is over here. Always ensure that whatever's detecting the sound is to the right of the source. Sound waves will be approaching the detector from the source, so the velocity of sound is always positive. Try drawing diagrams to confirm the term in brackets here behaves as you would predict based on you have learned about the Doppler effect. Notice that for a source moving toward the detector, positive direction, which results in a smaller denominator compared to the stationary source, and for a detector moving toward the source, negative direction and increased numerator compared to the stationary detector. The detected frequency increases. Similarly, if the source is moving away, FD should decrease. So if they're moving closer to each other, the frequency should be higher compared to what it was originally, and lower if it is in fact moving away. So we'll do an example here. Then I'll give you some hints in terms of the diagrams for the assignment. So here we have a car. It's moving to the right. Here's the detector right here. Detector. Source. So a trumpet player sounds C above middle. So it's above the middle C. So it's 524 hertz while traveling in a convertible at 24.6 meters per second. If the car is coming towards you, what frequency do you appear to hear? So we can look at all those variables. We have FD, we have FS, we have the velocity of sound in air that day, we have the velocity of the source, and then we have the velocity of the detector. So the detector is not moving, so that is 0. The car is moving 24.6 meters per second, and recall that This is going to be the positive direction, then to the left is negative, just like a number line. So plus 24.6. We'll have to figure out the velocity of sound that day. We're told that it's 20 degrees. So if we recall from that earlier formula that we had, to figure out the speed of sound in air, by knowing the temperature, we can do that quite easily. 331 plus 0.6 for every degree C it is above 0. So in this case, we have 20. It's at 20 degrees, so that's 0.6 taken 20 times. That's going to give us 343 meters per second. So 343 meters per second. The frequency of the source, it's an octave above middle C, so 524 hertz. And FD is what we're in fact looking for. So using that equation, okay, so we have Fs is 525. Speed of sound in air that day, 343. And then the detector is not moving, so that's 0, and this is going to be 24.6. Minus a positive is negative. So on top we have 343. On the bottom we have 318.4. And when we multiply that all out, we get 564 hertz. So that makes sense because it's moving towards us. So the waves will get bunched up. So our frequency that we hear should be higher than the frequency that's actually being made. So it's 524, which is actually being made. So the people in the car moving with it hear 524, but someone that it's approaching would hear 564. All right. In the next video, we'll go through over some hints for the assignment, sketch some of the diagrams that you're going to need.